Hi there. I'm going to finish up, I hope, this lecture on section 4.3. Um, we left off, we were talking about this function and we had found the derivative and we found the critical points, x equal 1 and x equal 3. That makes the derivative equal to 0. And we notice that the derivative is not defined at x equal 2, but that's not a critical point because that's not in the domain of our function. But it is an important thing to realize that x equals 2 is a vertical asymptote. So you do need to check on either side of a vertical asymptote because sometimes a function will change from increasing to decreasing there. So this is what we found. We're increasing from negative infinity to 1 and from 3 to infinity. And then we're decreasing from 1 to 2 and from 2 to 3. And the test intervals, if you do it this way, gives you a nice visual. I can see that at x equals 1, I have a local maximum. Because my graph is increasing, then I have a horizontal tangent, and then my graph is decreasing. Likewise, I can see that at x equals 3, I have a local minimum. So we need to find the y values at x equals 1 and at x equals 3. So sometimes students get confused here. The point is on the graph of g, so we need to evaluate g at 1 and g at 3. So let's do that over here. G of 1 would be 1 squared, which is 1, minus 3 over 1 minus 2, and that's going to be negative 2 over negative 1, which equals positive 2. G of 3 will be 3 squared is 9 minus 3 over 3 minus 2. That's 6 over 1, which is 6. So we have a local minimum of 6 at x equals 3 and a local maximum of 2 at x equals 1. And you might be wondering, how can the minimum be bigger than the maximum? Well, remember, these are local. So let's go look at the graph and see what's going on. Okay, so here is the graph of our function. G of x equals x squared minus 3 over x minus 2. Is that right? Yes. So, do you see why this is a local minimum? In a region around x equals 3, this is a local low point. And this point is a local max. Because around x equals 1, this is a high point. And this is kind of a strange looking graph um, because this is a rational function with a slant asymptote, or oblique, sometimes we call it. And that is the line that's not on the graph, but you can sort of visualize it here, and that's what the graph approaches as x goes to positive and negative infinity. How do we find the equation of that line? Well, maybe we'll do that. We have to use long division. It's a good thing to do. So let's find the equation of that line. Let's do that here. So to find a slant asymptote, we are going to use long division. And let's see how this goes. So we have x minus 2 divided into x squared plus 0x minus 3. Why do I have that 0x there? Well, if you're missing a term, you have to add it in, or the long division won't work. Now, you ask yourself, what do I need to multiply this x by to turn it into x squared? Or another way to look at it is, what is x squared divided by x? Well, that just equals x. So that's the first term up here. Then we multiply and we get x minus 2x. X squared minus 2x. And then we subtract. So x squared minus x squared, that is 0. 0x minus a negative 2x is plus 2x. And we will rewrite that without the 0. So I have a positive 2x down here, and I bring down the negative 3. And now I ask myself, what do I need to multiply x by to turn it into 2x? Or alternatively, you divide 2x by x, and that equals positive 2. So we don't really need to do this next step, but we're going to multiply again, just so you remember how this works. That would be 2x minus 4, and then we subtract. Remember, there are parentheses here. So 2x minus 2x is 0, minus 3 plus 4 is 1. So we have a remainder of 1, but this is what we're interested in. The slant asymptote is y equal whatever you get up here. Yes. So let's go back and look in the graph and see if that makes sense. Yes, here is 2, and I can see that that would be where the y-intercept is. And this does look like it has a slope of 1, this line, if you could imagine it. So that's how you find a slant asymptote. And we may be using long division to determine end behavior. So if you need some help with that, I have a handout that has a step-by-step guide how to do it. Maybe we'll go over that. Okay, so now we have another problem to work. Remember what we're doing. Finding critical points first. But I'm going to ask myself, what's the domain first, because I always like to do that. Well, how do you want to do this? This can be a little tricky. We need 25 minus x squared to be greater than or equal to 0. Well, this factors into 5 minus x, 5 plus x, greater than or equal to 0. Now, there are other ways to tackle this problem. This, if you write this as an equation, when will this be greater than or equal to 0? Well, what is this? That is a parabola that has been flipped, rotated around the x-axis, and shifted up 25 units. And what are these 2 points here? Do you know what they are? This are the zeros, negative 5 and 5. So if you can figure out this, that's what I see, then I know I'm going to be greater than or equal to 0 between 5 and 5. And that's my domain. Well, maybe you don't see that and you want to know how you're supposed to figure out this. Well, this is again is a test interval thing. The zeros are -5 and 5. You don't really get to spend enough time on this in pre-cal, but this is how we solve a quadratic inequality using critical points and test intervals. So I need to test the sign of this expression in each of these intervals. So test -6, test 0, and test +6. Again, you're just looking for the sign. So if I put -6 into the first factor, that would be 5 minus -6. That's going to be positive. If I put it into the second factor, however, it's going to be negative. So overall, I'm negative in this region. Now, we're just checking. This is not the derivative. We're checking for the domain. So we're not talking about increasing and decreasing. We're talking about the sign of the expression under the square root. And you can see it is negative over here, below the x-axis. When we put in 0, of course, we get positive times positive, which is positive, and that's the region in here. And when we put in 6, we get negative times positive, which is negative, and that's the region out here. So all this was to find the domain. So now I can say that the domain of this function is -5 to 5. Now another way, yet another way to realize what this graph is. What does this look like? Well, square both sides to make sure, because I think we're looking at a semicircle. So this is the upper half of a semicircle. So then you can figure out, oh, well, it's going to have intersect the x-axis at the radius 5 and -5. So many ways to figure out the domain of this function. You pick the one that works for you. And now let's get down to the real business. Of finding the critical points. So we need the derivative. Well, I think some of you have done as I suggested and memorized what this derivative would look like, but say you haven't. So let's do it with the power rule. 1/2 times 25 minus x squared to the -1/2. And don't forget this is an inside function. And from the chain rule, we get times -2x. So now we need to simplify. And this will become -x over the square root of 25 minus x squared. So what happened to this 1/2? Well, it got canceled by the 2. Where did this -1/2 go to? Well, that's a square root in the denominator. Now, when does this equal 0? Well, this equals 0 when x equals 0. That's the only time. So my critical points are x equals 0. Now notice the derivative is not defined at 5 and negative 5, but these are not interior points of the domain. So they don't count as critical points. But they are important when we have to check them when we're looking for extreme values, because we have endpoints of our domain and we want to check them. They're x equal negative 5 and x equal 5. So we have to keep that in mind. And now we're going to set up our test intervals. Okay, so we need another page for that. Let's go over here and set up test intervals. Now, I like to remind myself that we do have endpoints to this domain, so we don't want to check beyond negative 5 or positive 5. And 0 is right here in the middle. That's a critical point. So I need the sign of the derivative on either side of x equals 0. So let's test negative 1 over here and positive 1 over here. So f prime of negative 1, if you put that in there, that's going to be positive, isn't it? Because negative of negative 1 is positive. This denominator is always positive because it's a square root. Now, square roots can equal 0, but not when they're in the denominator. So I'm positive here. That means my original function is increasing. Plug in positive 1 into my derivative, and that's going to be negative. So I am decreasing here. So now I know that my original function, f, is increasing on negative 5 to 0 and decreasing from 0 to 5. F also has a local and absolute maximum at what? At x equals, oh, we need to say of, because that won't do it the same way every time. Of blank at x equals 0. Well, f of 0 is pretty easy to figure out what that is. That is 5. So that's, how did I know it's an absolute maximum? Well, because my function starts off somewhere at negative 5, it increases, goes to 0, and then decreases, and it never turns around and increases again. So that can be a little tricky, but we're not done. This function, guess what? It's continuous on a closed interval. So by the extreme value theorem, f has both an absolute max and an absolute minimum. So we found the absolute max. How do you think we're going to find the absolute minimum? We're going to test we're going to test the endpoints and see what happens there. Because remember, we said we we're going to do that. We got to check the critical point and the endpoints. From my test interval, I know that the maximum occurs here at x equals 0. So the minimum is going to be at one or both of these endpoints. So plug them in. What is x of -5? What is f, of 5 and -5? Well, if you square -5, isn't that 25? And if you square 5, isn't that 25? So f has an absolute minimum of blank at x equal 5 and x equal -5. So the value is 0, and it happens at 5 and -5. Now, it really is helpful if you remember what the graph of this function looks like once you realize that it's a semicircle. You hardly even need the derivative. You know this goes through y equals 5. So there's our absolute maximum at 0, 5. And here are our minimums. And there we go. And I think that's it. Finally. Probably way more information than you wanted. So now you need to try the examples and try the homework, book and Canvas, and let me know if you have any questions.